You may know from cartoons or from movies that most telescopes happen to be on top of mountains. The reason for this is many-fold. I mean, one, light from nearby towns tends to mess up telescopes, and so by going way out in the country, way up in the mountains where there aren't many cities around, you can get away from the lights. But also, telescopes tend to be above much of Earth's atmosphere and much of the blurring that the atmosphere causes. Here's a picture I took. I was at a telescope down in Chile called the Las Campanas Observatory, and I was looking out from the telescope out across, and you can see this layer of haze here just below the summit of this telescope. You can see that these shorter peaks are shrouded in haze, but nearby it's pretty sharp with no haze. In fact, this peak right over here is another observatory run by a European consortium, and you can see that its peak is just above this layer of haze. So by getting above the haze, you can see things more clearly, and also by getting above 6,000 or 7,000 feet of atmosphere, you avoid a lot of blurring. As I said, Earth's atmosphere causes light to be distorted, and that's just because of turbulence in the atmosphere. If you've ever been in an airplane and a little bit of chop, if you get up high in the atmosphere, that sort of turbulence happens at all different levels of the atmosphere. And if you look through it, your light is going to get bent. Even on a very still night, at the best sites that we can get to for telescopes, the absolute limit from the ground is about 1/2 arc second. The atmosphere will blur everything smaller than 1/2 arc second. So if you want to image things sharper than that, if you want to be able to see things with finer detail, then you need to do something else. You can't just look through Earth's atmosphere with a plain old telescope. Here's a movie of a star taken through a telescope. We've zoomed in really close, and all of this motion that you see and the noise, those little dots kind of swirling around the star, the back and forth motion, that is all caused by the atmosphere. The telescope's not shaking, the camera's not shaking. This is all bending of light by the atmosphere. So if you want to get a really sharp picture of the star, we need to somehow get rid of all of this crud caused by turbulence in our atmosphere. We have a few options for how to deal with that. One option is to put a telescope outside the Earth's atmosphere. That's what we did with the Hubble Space Telescope. The Hubble telescope, as telescopes go, is not a huge telescope. It's 2.5 meters in diameter. That's about 7-8 feet, which sounds large, but compared to the 10-meter Keck telescopes, it's pretty small. But because it's above Earth's atmosphere, it can see things much sharper than from the ground. The Hubble telescope can see to 1/20th of an arc second, which is about a factor of 10 sharper than any telescope from the ground. This sharpness is not because the Hubble telescope is in better focus. It's because the Hubble telescope doesn't have an atmosphere blurring the light on its way down. The main problem to space telescopes is that they are really expensive. The Hubble telescope cost about $4 billion. NASA is building a new space telescope called the James Webb Space Telescope, and this telescope will, by the time it's all said and done, have cost about $8 billion. That's just a lot of money. The Keck telescopes in Hawaii, which are much bigger than both the Hubble and the James Webb Space Telescope, they each cost $250 million, which is still expensive, but for the price of a Hubble, we could have built nearly a dozen Keck telescopes. Now the second option is relatively new. This is something called adaptive optics. And what we do is we take a laser and we shoot it up into the sky, and it makes a fake star way high in the atmosphere. Then we can use a computer to look at the light from this star. So the light comes down from the star, from the fake star, bounces to a little computer terminal that figures out how much the light has been blurred by the atmosphere and determines what it needs to do to take out that blurring. Then we have a little tiny flexible mirror that this mirror can be distorted to take out the exact opposite of the blurring that the atmosphere put in, and so at the very end you get a very nice sharp picture. So here's an example of adaptive optics as used on the sun. You can see at the very beginning it was very blurry. That was before we turned on that little flexible mirror, and here this sharp image is as it is at the end. So let's watch it through again. Blurry just because of the atmosphere, then we turn on the flexible mirror and we get a very sharp image. There's still a little bit of waving around caused by the atmosphere, but we can deal with that. The lasers that allow telescopes to do this adaptive optics are very impressive, and they can be seen from miles away. Sometimes it looks like there are lightsabers coming out of the telescope domes. So if you go back to eCollege, after these mini lectures I put a link to a YouTube video that shows some time-lapse photography of lasers on telescopes in Hawaii, and it sets it to the music from Halo. So you get a little dramatic music and some great pictures of lasers and stars and whatnot. So I'd suggest you go ahead and take a look at it. Here are some pictures of telescopes that I have used. And these are all pictures that I've taken myself. This picture is of the Magellan telescope, named after the explorer Ferdinand Magellan. It is located in Chile, in South America, and high in the Andes Mountains. Here we are right after sunset. You can see a thin crescent moon in the sky, and we are getting ready for a fantastic night of observing. This is a cousin to the Magellan telescope. It's called the MMT. Used to stand for multiple mirror telescope, because this telescope used to have several mirrors that combined the light, but they've since refurbished it and replaced it with a single big mirror. And this one is located just south of Tucson on a mountain called Mount Hopkins. It's about, both the Magellan telescopes and the MMT are about 6.5 meters in diameter. So they're among some of the largest telescopes in the world. This is the 82-inch telescope at McDonald Observatory. McDonald Observatory is in West Texas, near Big Bend. If you've heard of Marfa or Alpine, it's near those areas, a couple hundred miles east of El Paso, pretty much in the middle of nowhere. This telescope was built in the 1930s, and it still is run by a lot of the original motors and gears, so it feels like you've gone back in time when you use the telescope. But we do have modern cameras on it, and it's still a very valuable and useful telescope. I have used the Keck telescope. This is that same picture we saw earlier, the 10-meter telescope, largest telescope in the world. You can see that this telescope has a bit of a honeycomb design instead of just a single mirror. Each of these honeycombs is about 1 meter across, a little more than that, 1.5 meters across. And these individual mirror segments are a lot easier to deal with. So if it gets dirty, we can take out the one dirty segment, put a new one back into place. And each of these mirror segments is separately controlled by a computer, so that we can keep the mirror in the absolute perfect shape all night long. And it's really quite a technological marvel. And this segmented structure is a less expensive way of getting a very large mirror. So to summarize optical light telescopes, a telescope is used to focus light, usually to a camera. Refracting telescopes are telescopes that use lenses to bend the light, but because we are using lenses, they're limited to about 40 inches in diameter. Reflecting telescopes use mirrors, so you can support it all around, and these are the most common kind of telescope that are used by professionals. The main purpose of having a large telescope is to collect more light. A larger diameter telescope will collect more light, and that light gathering power is related to the area of the mirror. And since area goes as the radius squared. If you double the diameter of a mirror, you quadruple the amount of light. If you triple the diameter of a mirror, you will increase the amount of light you're getting by a factor of 9, and so on and so forth. Larger telescopes can also see sharper images if you can get rid of the atmospheric blurring. So you can get sharper images by going to space, and the bigger telescope you have out in space, the sharper your view will be. And you can also get sharper images from adaptive optics. That's from putting the laser on the side of the telescope, making a fake star, measuring how much the atmosphere has blurred light, and then using computers and a bendable mirror to take that distortion out of the light that's coming in. So that completes this mini lecture. Please go and complete the response questions to this mini lecture before going on.